Greetings to all from Nairobi, Kenya. Welcome to the fourth seminar in this series. Warm regards to all. So, as some of you attended the last seminar, we had Damari Zodeni presented us with the numerous applications of genotyping on sorghum. And we had a lot of good feedback from all the presentations. And today we have a young scientist from the CSR SARI, Ghana, Dr. Charles Lenimore, and he will let us know what is going on in his research on maize in West Africa. And his work is focused on heat tolerance. So as the previous sessions, and before we start today's presentations, we are very pleased to welcome Dr. Melaku Gedil. He is a molecular geneticist working with the Maize IITA and located at Ibadan, Nigeria. He has a huge experience in genetics and molecular marker applications through his extensive career, and he will let us know a bit more about his work and present Charles to us. Please, Melaku, please go ahead.
So can you see my presentation now?
Not yet. Are you able to share?
Yeah, I did.
Okay, it's started.
It's sharing now? Okay.
Yes, thank you, Melaku.
Yeah. Okay, what is this window? Okay, it's fine. Yeah, thank you all. I'm privileged to be the producer of the speaker of today's seminar. Actually, I was supposed to attend all the previous seminars, but somehow it clashed with other engagements. So this is my first seminar in the series. As Anna said, my name is Melaku Gedil. I'm based in IIT Nigeria. This seminar is about maize. So I don't want to bore you with the importance of maize globally. Most of you know, but just a few words about the importance of maize in West and Central Africa. It's a staple crop for millions of people in West Africa. It's contributing substantially to regional food security. It has several uses. One of them is a staple crop. As a staple crop, it's consumed as porridge, dough, maize meal, and also nutritionally, it is combined with other crops to provide balanced diet. Secondly, as a source of income, traders sell flour, maize oil, and animal feed, and this augments the rural economy. Another use is in the farming system. Maize is adapted to diverse climatic conditions, so it is grown in combination with other crops in crop rotation and in other systems. Okay, how do we continue now? The next slide. Importantly, maize has a cultural significance. In many West African societies, it's often incorporated into traditional ceremonies, rituals, and cuisine, reflecting this deep-rooted importance in local cultures. Therefore, that makes it an integral component of the region's food system, the economies, and the culture. So in short, or in summary, maize ensures food security in West and Central Africa. It provides livelihood, and it enhances resilience to environmental challenges such as drought and heat. So the focus of maize improvement in the region, both in the CG centers, in the NARS, in partnership, these are some of the key stresses. We can see that the focus is one of the focus is reduced toxicity. Example is aflatoxin, reducing aflatoxin production in maize varieties. Biotic constraints, including maize streak virus, maize lethal necrosis, fall armyworm, and striga. MLN is not presently in West Africa, but we do pre-breeding for MLN, preemptive breeding for MLN using marker-assisted selection. Another area is nutritional quality, supported by Harvest Plus and other initiatives. We breed for vitamin A, zinc, and the main goal, which is productivity, is reducing yield gap. The yield gap in maize, like in other crops in developing countries, very, very high. So we want to reduce that. But today's focus is adaptation to soil and climate change, which Charles is going to talk about, is heat tolerance. There are some studies on drought and heat, low N, or combination of these traits. So we'll hear more details about the heat tolerance later. But one of the things I want to emphasize here is with regard to the crops to end hunger support from the EIB support, the role of genomics intervention in the breeding workflow. So we use genomics in every aspect of the breeding workflow, but today's seminar is mostly in the pre-breeding part, in the diversity analysis, in the characterization part. So you will hear more details about that because I don't want to spend much time explaining that, but I just want to say that genomics now is fully integrated throughout the workflow of the maize variety development or cultivar development. So recently, there is a shift in breeding focus. Instead of just working on a single trait, we are working on combining tolerance to multiple stresses. It could be biotic, it could be abiotic. So in terms of climate change, there is severe and frequent droughts in the region. There is high temperature, so you can have a combined effect of both. And on top of that, you can have biotic stress such as striga. Striga hermontica is very important in the region. So farmers frequently face the co-occurrence of drought and striga. Usually striga's effect is pronounced when you have drought. So combining tolerance to drought with resistance to striga is very, very important. So a number of varieties have been developed to mitigate these problems. I just have one slide to show here the genetic gain made in across the years. So you can see that since the turn of the centuries, there is great improvement in yield, while some of this increase in yield may be through increasing the area of production, but genetic factor, introduction of improved varieties has promoted the spread of this crop. So there is really very good progress in that area. So this brings me to today's seminar, which is going to be presented by Dr. Charles Nellimore on the topic of genetic and morphological characterization of maize landraces for heat tolerance. So Charles embarked on DAAD ClimeMap Africa, Climate Change Research in Africa Fellowship to study the mining of maize landraces for West Africa climate resilience. Today, he will let us know what he's doing in his talk on this genetic and morphological characterization of maize landraces for heat tolerance. So with that little introduction, I hand over to Charles to give his seminar. Thank you.
Okay, thank you.
Charles, can I share?
Yes, you can.
Yeah.
Okay, okay, you stop the
it's everybody seeing the screen?
Yes.
Charles,
Yes.
Go ahead, please.
Okay. Sorry about that technical challenge. Good morning, good afternoon, and good evening, depending on your location. So this afternoon here in Ghana, I will be talking on the genetic and morphological characterization of land-raised genetic resources of maize for tolerance to heat stress. I am Charles Nellimore. Please change the slide. Next slide. Okay, so this is the outline of my presentation. I'll first give a brief background to the study, where I will highlight the objectives that we seek to achieve.
Hello, Charles. We lost you.
Yes, cannot hear him. Hello.
Yes, now we can hear you. Please, can you start?
Yeah, I can't see my slides either. I can't see the slides.
Can you see it?
Yeah, I can see it now. Good.
Okay, yes.
So I'll be sharing with you the preliminary results of our study. Then based on the preliminary results, I will draw conclusions. And these conclusions may not be conclusive enough because the study is still ongoing. And then I will highlight the perspectives of our study. Please, next slide.
Turn off one of your device. When you have two, you get echo. Maybe you can turn off the computer, yeah.
Okay. All right, I think the computer is off now. Okay, next slide.
Yes, please go ahead.
It's not showing on my.
Yeah, it's about the background.
Oh, okay. I'm still waiting for it. Anyway. So
it's a map. So maybe you can open the
yes.
your computer and talk about it.
Yeah. Okay.
It's a map, the African map.
Okay. So climate simulation studies have demonstrated that by the end of this century, air temperatures in large areas of sub-Saharan Africa will most likely increase by between 2 and 3 degrees Celsius. Precipitation, on the other hand, is expected to be erratic, with drastic decline in rainfall amount, intensity, and duration. So the fluctuation in temperature and rainfall patterns will likely result in extreme climatic conditions such as drought, floods, and heat waves, depending on the location. Consequently, the growth and the productivity of the major staple food crops within the region would decline drastically, and this could lead to severe food insecurity issues. So global climate change therefore represents a major impediment to the attainment of food security and sustainable development goals in sub-Saharan Africa. Please, next slide. Okay, so maize is one of the most important staple food crops in sub-Saharan Africa, where more than 50% of the population depends on it for food and economic security. However, despite its importance, the growth and the productivity of maize in this region is highly vulnerable to climate-induced stresses, particularly drought and heat. It has been demonstrated that all stages of the maize plant is susceptible to climate-induced stresses, but the reproductive stages, which spans a few weeks before flowering to a few weeks after grain filling, is the most sensitive. Studies have shown that when drought and heat stress coincides with the reproductive stages of maize growth and development, grain yield losses can be more than 40% under mild conditions. And under extreme conditions, these two stresses can force farmers to abandon their farmlands. It has also been demonstrated that a 2-degree rise in temperature will most likely result in much greater yield reductions in maize as compared to a decline in precipitation by 20%. Recently, Keynes and others also demonstrated that for every 1 degree rise in temperature, the grain yield of maize reduces by 1% under optimal rain-fed conditions and by as much as 1.7% under drought conditions. So these studies are a testament to the negative impact of heat stress on the growth and productivity of maize in this region. Perhaps the most economically sustainable way to adapt maize to climate change is to develop maize varieties that are resilient to climate-induced stresses, particularly drought and heat. The land genetic resources of maize are with tremendous genetic variability, and as such, they harbor beneficial alleles or genes that could be harnessed for maize improvement for adaptation to climate change. But for us to effectively use landraces in genetic improvement, they must be systematically characterized for target traits. Next slide, please. Hello, next slide.
Charles is already in the genetic materials.
No, please. I'm not done with the objectives, and I can see that here. So it is against this background that our current study is being undertaken in order to contribute to the discovery, characterization, and deployment of novel sources of gene variations that confer the resilience of maize to climate-related stresses. Specifically, we seek to identify landrace accessions that have high value for climate-adaptive breeding of varieties that are needed by farmers, and also to elucidate or to decipher the genetic architecture or the genetic base of drought and heat adaptive traits in order to identify favorable alleles or genes or haplotypes that could be deployed in genomics-assisted breeding to accelerate the development of climate-resilient maize varieties upon validation. So for the materials and methods, we assembled a diverse panel of 250 landrace accessions of maize from national and international gene banks. Of the 250, 145 were supplied by the Genetic Resources Center at RITA in Ibadan, Nigeria. 100 were obtained from the Plant Genetic Resources Research Institute at Bonso here in Ghana. And then the remaining 5 were supplied by CIMMYT Germplasm Bank. So about 100 seeds of each of these maize accessions were obtained, and then the seeds were multiplied at the breeding nursery here in Sari in August 2021. So after successful seed multiplication, a panel involving 210 accessions was constituted, and this panel was used for the study. Please, next slide. So the maize panel of 210 accessions were evaluated under heat stress conditions at Botanga. Botanga is located within the Guinea Savannah agroecological zone of Ghana, where extreme temperatures, which usually ranges between 31 and 45 degrees Celsius, occurs during the dry season. So at Botanga, the trials were planted in mid-February this year, and then the flowering and the grain filling stages coincided with extreme temperatures which occurred in the month of April. So a furrow irrigation system was used to supply water to the plants from planting to physiological maturity. Then as control, the same set of maize germplasm were evaluated at Nyankpala and Damango during the growing season of 2022. So these locations, that is Nyankpala and Damango, they are also located within the Guinea Savannah Agroecological Zone of Ghana. So under each of these conditions, the trials were laid out using alpha lattice block designs with 2 replicates. The experimental unit consisted of single row plots that were 3 meters long. Then the distances between the plants within a row were 40 centimeters, while the rows were kept at 75 centimeters apart. So we planted 3 seeds, and later on we turned to 2, which gave us a total plant population density of about 66,667 plants per hectare. The weed control, fertilizer application were all carried out. Then at various stages of plant growth and development, data was collected on plot basis for flowering traits, plant architectural traits, and then grain yield and grain yield related traits. We also collected data on weather parameters during the period of the study. Please click on. Okay, so 2 weeks after planting under optimal growing conditions, leaf samples were harvested from 10 to 15 individual plants per accession. These were bulked to form composite samples, which were then dispatched to Intertech laboratories in Australia through the EIB platform. So in Australia, the genomic profile of the maize germplasm was determined using the mid-density genotyping platform, where a total of 3,305 dissect markers were used. Please, next slide. Okay, so the data that was generated from the optimal growing conditions at Damango and Nyankpala, and that under heat stress, were analyzed for analysis of variance using SAS statistical package. Then from the analysis of variance, we extracted the variance components, and these variance components were used to calculate the broad sense heritability of the traits. We also extracted the bloops, which was then used as a data set to construct a phylogenetic tree that depicted the genetic relationships among the maize accessions. Then promising maize accessions under heat stress were identified by using a base index that was proposed by Bedu, Apreku, and others in 2015. So this base index basically made use of grain yield under the stress condition and 5 other secondary traits, that is EPP, which is years per plant, anthesis-seeking interval, which has to do with the difference in days to female and female flowering, then plant aspect, ear aspect, and then stay green characteristics, which were all scored on a scale of 1 to 9. So the traits were first standardized, and then after that, they were imputed into this formula. So at the end of the day, accessions which recorded positive base index values were identified to be tolerant to the heat stress that was imposed, whilst those with negative base index values were classified to be susceptible to the heat stress that was imposed. Next slide. Okay, so the data that was generated from the genomic profiling of the maize germplasm was subjected to quality processing, in which markers with minor allele frequencies of less than 5% were eliminated. We also filtered out markers with missing data or missing rates of more than 20%, as well as assertions with missing data of more than 20%. So after the filtering, the high quality data that was obtained was subjected to various genetic diversity analysis, which included analysis of genetic diversity parameters, such as observed and expected heterozygosity, then polymorphic information content, all using the power marker software. The data was also subjected to cluster analysis using 4 complementary clustering methods. That is population structure using the structure software, principal coordinate analysis using the GeneAlex software, and then a neighbor joining tree, which was constructed using the power marker and then viewed using the fig tree software. Then we also performed a DAPC analysis using the R software. Next slide. Okay, now the results and then discussion. So figure 1 here is showing the weather conditions that prevailed during the flowering stage of our study. We observed that the night temperatures during the entire flowering period were all above the threshold temperature of 25 degrees Celsius. Similarly, the day temperatures too were all above the threshold temperature for maize growth and development, which is 35 degrees Celsius, with some of the days recording as high as 42 degrees Celsius a day. So there were some minor incidences of rainfall, but these were negligible to affect the results of the study. So this observation indicated that our maize germplasm were subjected to extreme heat stress, which were all above 25 degrees Celsius minimum, and then the maximum were also above 35 degrees Celsius. And therefore, any differences that we observed can be attributed to the response of the maize germplasm to the heat stress that was imposed. Next slide. Okay, so table 1 here is showing the grain yield and other traits of the best 10 and the worst 5 assertions that were evaluated under heat stress conditions at Botanga. So there were highly significant differences among the maize assertions for all the traits that were measured, indicating that our maize germplasm harbored ample phenotypic diversity, which should allow us to identify promising assertions both under non-stress conditions and under heat stress conditions. The broad sense heritability of the traits were moderate, and this is typical of broad sense heritability estimates under stress conditions. Then grain yield on the average under non-stress conditions was 2.86 tons per hectare, and that under heat stress conditions was approximately 1.7 tons per hectare. And this translated to a yield reduction percentage of 41%. And this yield reduction is within the ranges that have previously been reported for maize under heat stress conditions. So the antecedent interval of the best assertions were narrow as compared to the worst assertions, which recorded delayed or extended antecedent interval. The promising assertions also recorded desirable plant and ear aspect scores and increased number of ears per plant as compared to the worst assertions. Then the tassel blasting and leaf firing symptoms of the promising assertions were very low compared to the worst assertions, of which some of them even recorded leaf firing and tassel blasting of 100%. So based on the index selection, which ranged from 13.61 to about negative 31.5 now, a total of about 55 landraces were identified to be promising as donors of heat stress tolerance. Next slide. Okay, so leaf firing and tassel blasting are 2 important physiological traits that are often observed when maize is being subjected to extreme heat stress. In our study, the occurrence of these symptoms was very common. So we decided to find out the contribution of these traits to the yield reduction that was observed. So to do so, we regress grain yield on each of these traits And we observed that the R-square values for each of these traits was 0.30, indicating that each of these traits contributed approximately 30% to the yield reduction that was observed under heat stress. And this 30% is slightly higher than the 28% that was recorded by Meseka and others in 2018 when they evaluated a set of maize germplasm under heat stress conditions. So this observation indicated that these traits, that is leaf firing and tassel blasting, are very important, and therefore they should be considered for inclusion in index selection for heat-tolerant maize varieties. Next slide. So we then combined the leaf firing and tassel blasting data to the traits that were used in the index selection, that is grain yield and the 5 other secondary traits. So these were combined to form a data set, which was then used to construct a phylogenetic tree, which depicted the genetic relationships among the maize accessions. Please click on. So the results of the phylogenetic tree classified the maize germplasm into 3 main genetic groups. Please click on. Into 3 main genetic groups. So the first group, which is represented by the red color here, was composed of 90 landrace accessions. Please click on. 90 landrace accessions, which exhibited high leaf firing and tassel blasting symptoms. And as such, they recorded barren ears. Then the next group, which is made up of the green color here, was composed of about 60 landrace accessions. Please click on. So this group was made up of 60 landrace accessions, which showed a poor grain filling ability. Then the third group here was composed of about 55 landrace accessions, which recorded desirable plant and ear aspect scores with increased number of ears per plant. So by looking at the summary statistics of the various genetic groups, we realized that all the individuals of cluster 1 and those of cluster 2, they recorded negative base index values, which indicated that the members or the individuals of these groups were susceptible to the heat stress that was imposed. Then all the individuals of cluster 3, we realized that they recorded a positive base index values, and as such, they were tolerant to the heat stress that was imposed. So based on this, it can be concluded that our maize germplasm clustered according to their level of tolerance to the heat stress that was imposed in our study. And this clustering pattern is similar to those that have previously been reported for maize under drought and heat stress by Meseka and others, and Tanji and others in 2018. Please click on. So to confirm our results, we genotype our maize panel with 3,305 high-quality dissect markers. And after filtering for markers with minor allele frequencies of less than 5% and missing data of more than 10%, a total of 2,405 high-quality dissect markers were retained. And these were used for the various genetic diversity analysis. So the table 2 here is showing the summary statistics based on the 2,405 high-quality dissect markers. And because we also filtered for accessions with missing data, 7 of our accessions were filtered out, leaving 210 accessions. So the results show that the minor allele frequencies of the genetic markers ranged from 0.5 to 0.95 with an average of 0.72. Then the gene diversity, the heterozygosity, and then the polymorphic information content values averaged 0.37, 0.51, and 0.29 respectively. And these values are considerably high, confirming that the maize germplasm that we evaluated harbored ample genetic diversity. And these values are within the ranges that have previously been reported by Nelimo and others in 2020 and Badua-Preku and others in 2001. Next slide. So the figure here is showing, or is the graphical representation of the population structure of the maize panel that we evaluated. So the results of the population structure showed a peak. Please click on, showed a peak at 3. Yeah, showed that the delta K value plateaued at 3, which indicated that the maize germplasm can be divided into 3 main subpopulations. Click on. So by using a membership coefficient or a membership probability of 80%, about 120 of our assertions, which represented 59%, were successfully assigned to the 3 subpopulations, whereas the remaining 41 were classified as admixtures. Please click on. So by comparing the individuals of the various subpopulations to the phenotypic data that were generated under heat stress, we realized that the majority, in fact, about 95% of the individuals of subpopulation 1 and subpopulation 3 were all susceptible to the heat stress that were imposed in our study. Please click on. But then we also realized that more than 80% of the individuals of cluster 3 recorded positive base index values, which indicated that the individuals of cluster 3 were tolerant to the heat stress that was imposed in our study. So based on this observation, we realized that the grouping of the maize germplasm, or the population structure of the maize germplasm, was concordant with the grouping that was revealed using the phenotypic data under heat stress conditions. Click on. So in summary, both the genotypic data and then the phenotypic data reveal that the maize panel that we evaluated harbored ample genetic diversity. And this genetic diversity enabled us to identify 55 landrace assertions, which could be which were promising as being tolerant to heat stress. But this observation of these 55 landraces were identified based on only 1 year data. And therefore, we seek to repeat this experiment in order to confirm whether or not these 55 landraces were indeed tolerant to heat stress. So based on the results of our study, we will recommend that tassel blast or tassel blasting and leaf firing should be considered for inclusion in index selection for selection of heat-tolerant maize varieties. So for the next step, once we finish with the phenotyping data, we will combine the genotypic data with the phenotypic data in an association mapping study. And this may enable us to identify genomic regions or genetic markers that are associated with important agronomic traits of the maize assertions. And these traits, I'm talking about tassel blast, leaf firing, and then the secondary traits that were used in the index selection. Then we will also conduct genetic studies once we confirm that the 55 landraces were promising. We will conduct some genetic studies to determine their combining ability and then extract Imbre lines from these assertions. And these Imbre lines could be used to develop hybrids that are tolerant to heat stress conditions. Please click on next slide. So I would like to acknowledge IITA, the Genetic Resources Center at IITA, the Plant Genetic Resources Research Institute at Bonsu, and CIMMYT for providing the maize germplasm that were used for this study. Then special thanks also goes to the EIB platform for genotyping the maize panel that we used in this study. And I also want to thank Dr. Anna for the technical support that she provided throughout the entire period of the study. Thank you all for your kind attention. So, Dr. Anna, I think I'm done.
Thank you, Charles. Thank you very much, really. Thank you for all the patience because all these technical issues. So we have some questions, and please, I didn't add the time to see if there is any questions. I'm checking, but just raise your hand. Yes, Damaris, and just unmute yourself, please.
Thank you so much, Charles, for your presentation. I have one concern with the data that you showed. Unless I didn't see clearly, are you saying that the heterozygosity of the markers you retained was 0.5? Could you please go back to that slide?
Okay.
Yeah, no, you passed it. You just passed it, that summary that has heterozygosity, PIC, MAF.
It's here, Damaris?
No.
I think,
back, so you go ahead now, I think. Ahead.
Please go ahead.
Ahead.
The next one. Yeah.
Yeah. The mean heterozygosity that you have in your genotypic data set is way too high and raises concern over the data that you have.
Well, the germplasm that we analyzed here are landraces. So their populations and the high heterozygosity was expected.
Well, but the thing is, you can
and we didn't filter because they were landraces. We didn't filter for heterozygosity.
But so how do you know if those are sequencing errors? I mean, this is DARSEC, and most of what you end up with would give you heterozygous calls if there's sequencing error. I think that's such a high level of heterozygosity. If you even say the maximum is 1, then that locus is absolutely not informative. In fact, if you could check, just do a small PC analysis and see how informative those markers are, chances are you'll find that you might have to get rid of the highly heterozygous markers.
All right, noted.
Okay.
So thank you very much for that observation.
Thanks for the wonderful work. Yeah, thanks.
Yeah, thank you.
Any other question? You may ask directly. Otherwise, I have a question, Charles, and because we don't have much time, we just have 1 minute. So people that have the questions can also write to us, and you can answer later. And we can put together with the video and the PDF that we will share publicly. So the question that I have is, Charles, what specific aspects should be taken into consideration when doing research in heat tolerance in maize, particularly under field conditions? Do you have any advice for colleagues that also want to do such kind of research?
Oh, okay, so some of the important factors you may want to consider when you want to evaluate maize under heat stress conditions include one, you may want to look at the site. The site selection is very important. So at least you should have the weather data of the site that we are choosing, at least for 10 years, to indicate that this site is indeed prone to heat stress conditions. Because without that, you are not going to get the desired results. And then moreover, the genotypes that you are going to evaluate, you should make sure that those genotypes are of the same maturity group. Otherwise, you are going to bias your results. And then when you are planting, you should time your planting in such a way that the flowering stage, which is the most important stage, will coincide with temperatures that are above the threshold for maize growth and development. Thank you.
Thank you, Charles. Yes, Melako, please.
Yeah, I know you want to close, but just quick question. Charles,
okay.
What you presented is a one location, 1 year phenotyping, isn't
yes,
it?
Yes,
So
yes.
what's the next plan? Is it still one location, another year? I know it's very difficult to phenotype for heat, but
yes,
is that your plan?
You know, yeah, so the plan is that next year we'll repeat the experiment at the same location. We would have wished to make it 2 locations, but national programs, you know, we are resource constrained. So we'll repeat the experiment next year to confirm these results.
Yeah, to get a good GWAS association, I think you should continue.
Yes.
You should strive to phenotype in at least more than one location, I guess.
More than one location. All right.
Yeah.
All right. Okay.
So Bodo have a question. Are the 3 groups in the dendrogram the same as the 3 groups in the Evano analysis?
Yes, the majority of them are in the same group. So it can be concluded that the phenotypic dendrogram and that of the Evano method were concordant in dividing the maize germplasm into 3 genetic groups.
Charles, to finalize, Alejandro is asking, any plans for testing under conditions of the locations where these MLRs are planted?
Come again, I don't get the question. Come again.
Any plans for testing under conditions of the locations where these MLRs are planted?
The last part, what?
The landraces.
Landraces.
Yeah.
So do you have any plans to test these landraces under the conditions of the locations where these were planted? I'm not sure, Alejandro, if this was the best way to ask.
Yeah, so this...
I still don't get the question.
Let me just say it. This comes from specific locations from different areas. So any plan for real life where these are actually planted and used, maybe the conditions where you're testing are not the most appropriate and they are having some difficulties in growing well just because they are not adapted to these conditions.
Are you referring to where the land races are coming from, the specific locations where they are coming from?
You have several.
Where they were collected from.
Correct, from where they're collected, simulating those conditions.
For now, no, please. We don't have that plan yet. It may be interesting to do that, but we don't have the resources to go to that extent.
Thank you. So, Charles, I think Cesar is just a suggestion. So maybe to do more locations, but also more markers to do the GWAS analysis. Cesar, if you want to unmute yourself, it's fine. Otherwise, we finalize the seminar.
Thanks, Anna. Yes, I believe that you will need more in this case to make a GWAS
are too far. You are too far from the speaker.
Hello, can you hear me there?
Yes.
Yeah, I can hear you.
Just a suggestion that maybe you need to increase the number of markers and maybe also number of samples to get a good result in the GWAS analysis and get the enough power to your computer.
Oh, okay. Actually, we evaluated about 310 of them, but for this presentation, I just extracted 200, a set of them for this presentation.
Okay, and in this work, in this analysis that you presented, very nice presentation. I think that you said that you prepare bulks. Did you?
Come again.
I guess that you said that you prepare bulks for this analysis that you presented. The sampling.
I'm not getting the last word that
you. The sampling. You did it using bulks.
If you mentioned
box samples. I use box samples.
All right, good. So the genotypic data, do you use scores, ones and zeros, or the counts and allele frequency?
Ones and zeros.
Okay.
It's a binary data set. All
right. Yes, in this case, when I use bulks, the genotypic data, that I prefer to use the allele frequencies calculated using the counts.
Okay.
Yeah, you have that option too.
Okay, all right.
Yeah.
Okay, thank you.
Comment, Anna, before we close on Cesar's recommendation. He said to increase more markers, but this DARTag version 2 is limited, maximum 3,000 is a panel. So I think I want to plead with EIB if we can increase the number from 3,000. I know there's a lot of logistic cost and everything implication to increase the panel to maybe 5,000, 6,000.
Excellent comments, because yes, my doubt was if you use DARTag or DARTseq, because in the presentation was DARTseq.
Oh, it's DARTag. I think he meant
okay.
All
right.
So it was utilized DARTag, and thank you for that comment. So it's something that if the Maize team reach to us, we can make a case, and if really there is a justification for that, it's something that we can start to initiate and to add more markers. So please just reach us and make these comments to us, please. Most welcome.
Okay, thank you.
Can I say something, Anna?
Yes.
So if this is DARTag, and he's using it, because my understanding is DARTag is more suited for genomic selection, and I would imagine for maize, you've put all the trait markers in there, so you can use it for genomic selection. But this study is actually for trait discovery, in which ideally he is paying. If EIB was not supporting, he would essentially be paying $12 per sample. For equivalent, he can actually do scheme-seq and get more data for the GWAS analysis than he would get from that tag. I'm just thinking aloud. So in that case, if this is actually tailored for GWAS analysis, probably that tag is not the best panel. But what can be done is just to look at the informativeness of the DARTag against his set, and maybe after doing scheme sequencing and identifying some associated markers, can come back and add those markers to the panel for eventual future genomic selection. Just thinking aloud. Yeah.
Thank you, Damaris. So, Mokhtar also made the same comment, and indeed the DART markers are not usually designed for GWAS studies, only diversity and for GS work. So I believe that, and Charles can confirm, I think the main work and the purpose that the EIB sustained this work was for an initial study of diversity. And like you said, after later on can add more markers and really can do the GWAS. But Charles can also to add something more, because he will need a much more higher coverage, like Mokhtar is saying. Charles, you want to comment?
Okay. Thank you very much. Thank you very much for the recommendations. I'll take that into consideration. So, Dr. Anna, I'll come back to you for the support.
Okay. Okay.
Yeah.
Thank you very much to all, really. We are really sorry for today's technical issue, but I think overall it went very well. Thank you for your patience, for your support. So we came to the end of the 4th seminar of this series, and the next seminar, there was a shift, because the next seminar that should be on the 5th October would be Patrick from IITA to present on cowpea. But due to one meeting that he will have, so we will have instead of him, Salej Wood from Simla, India, talking about the accelerating genetic gains through genomics-led breeding in potato. And Patrick will make his presentation on the 20th of October. So we will put this in the website. I also will try to fix the practical aspects of these technical issues, and probably will resend an invitation to all. So be here with us, and thank you very much for your support. Thank you.